Welcome to the second part of the Sun trilogy. If you haven't seen the first episode, hit the pause and watch it first. Let's keep things in order. If you have seen it, then you know that we ended the episode with kind of a promise that we'll try to explain how come that the surface of the Sun is cooler than its corona. I'm afraid I'll have to disappoint you, because this is still an open question in science. There are hypotheses, but there's no agreement as of now. The Sun is a ball of constantly moving electrically charged plasma. As this plasma moves, it creates heat waves. So these heat waves might make their way farther than the very surface of the Sun. Therefore, they might heat the corona. On the other hand, there's the Sun's immense magnetism, which is the main topic of today's episode. And magnetism can be another explanation why the corona is heated up to millions of degrees. The phenomenon, however, needs further research. Hopefully, we'll get the answer soon. The Sun's magnetosphere is something incredible. It can reach in form of a solar wind far, far away into the solar system. How this magnetosphere is generated? First of all, by the Sun's unique rotation. Layers and latitudes of our star do not rotate in the same way. While the pole's rotation takes 35 days, the equator's rotation is 25 days. Can you imagine if our Earth rotated differently at its equator and at Europe or North America or other continents? Continents would fall apart. The Sun is not a rocky planet, so there are no continents to fall apart. But this rotation, which in science is called differential rotation, caused something really strange in the star's magnetosphere. By this rotation, the magnetic field is stretched and twisted all the time. Imagine a string which you twist and create several knots on it. What would happen to it? It will snap eventually. The same happens with the Sun's magnetic field. And this leads us to what we call the solar cycle. It begins with the so-called solar minimum. It means that the magnetic field is more or less calm. Therefore, the Sun is more or less calm. But due to this rotation, as the magnetic field gets stressed all the time by the plasma, which rotates not only at different speed, but also in the opposite direction. So the magnetic field gets more and more unstable. The Sun gets more active. And how do we measure the activity of the Sun? With sunspots. At first, there are a few of them, and they emerge farther from the equator. But as we move forward in the solar cycle, there are more and more of sunspots, and they are closer to the equator. It's usually said that the solar cycle lasts 11 years, and it is true. What happens in the end of this cycle? The magnetic poles shift. The northern pole becomes the southern magnetic pole and vice versa. But to be more precise, the complete cycle takes 22 years. because in 22 years the poles are not only reversed, they rearrange themselves to their more or less original position. What are sunspots? We can observe them by looking at the sun with a telescope. We see dark patches, and these patches usually appear in pairs because they have opposite magnetic polarity. They appear darker, but in truth, it has nothing to do with their color. Let's make it clear how they emerge. When the magnetic field gets intense, it prevents convection. You can remember from the previous episode that convection is when plasma ascends to the surface, loses energy, and then descends again. The magnetic field suppresses convection. So plasma cannot make its way so easily to the surface. That's why the temperature drops. Why the photosphere is usually 5,000, 6,000 degrees Celsius. A sunspot is 3,500 or 4,500 Celsius. But it's not the end of the story. As the magnetic field is more and more stressed and the loops get more and more twisted, they eventually snap. And this snap was an explosion. And this explosion has the energy of billions of TNTs. By the way, compared to the sun's energy, the whole atomic arsenal of our planet, even if we are able to destroy us with our weapon multiple times, compared to the sun's energy, this is just a flap of a butterfly's wing. So when this immense explosion occurs, flares appear. These flares are visible light, X-rays, and ultraviolet radiation. They reach Earth at the speed of light, that is, in 8 minutes and 20 seconds. But as they reach upper layer of the atmosphere, they disturb the plane's radio communication. Flares are very spectacular, but they might seem harmless compared to CME, that is Coronal mass ejection. Coronal mass ejection means that tons of plasma is launched into space. Luckily, not all CME is launched toward Earth. They wouldn't exist probably if each of them would reach us. Some of them, however, reach us. And that's when our planet experiences magnetic storms. As charged particles from the sun interact with atoms and molecules of the upper layers of the atmosphere, they form something beautiful, that is aurora. During strong magnetic storms, auroras appear not only at the poles as usual, but at much lower latitudes. But that's nearly not all a magnetic storm causes. It disturbs satellites, navigation system, spacecrafts, aircrafts, and even transformers. A gigantic CME took place in 1859, and this is called the Carrington Event. On September 1, 1859, a British astronomer, Richard Carrington, was observing the sun with his telescope when he saw an incredibly bright flare. Of course, he had no chance of knowing what it would cause to Earth because this CME was launched toward our planet. 17 hours later, by the way, it takes from 15 hours to several days for charged particles to reach Earth. During the Carrington event, it happened in 17 hours. Auroras appeared in the Caribbean and Hawaii. They were so bright that people woke up in the middle of the night thinking it was day. They could read papers at this bright glow. Birds started singing because they thought the sun had risen. But there was a more dramatic consequence. A telegraph was the most advanced technology of that time. Currents were induced in wires. There were sparks, operators received electrical shocks, and even after the whole system was shut down, messages kept going. It means that the telegraph system was powered by solar energy. But however crazy it sounds, it wasn't the greatest magnetic storm in the history of our planet. And you may ask, how do we know if there was no advanced civilization before that and people hardly knew what magnetism was? But a really strong magnetic storm has a chemical fingerprint. In the upper layers of the atmosphere, the so-called carbon-14 and other isotopes are created, and later they can be detected either in tree rings or in preserved ice. Studying tree rings, scientists found out that there was a major magnetic storm in 774, 75, and 993, 94. And these are called the Miyake Events. Now imagine what would happen if a major CME was launched to Earth and such a great, incredibly great magnetic storm took place. The bad news is that it would be apocalyptic, because our civilization is absolutely dependent on electricity. If a damage was caused to power grids, there would be no water supply, no bank system, no transport. I'm not even talking about air transport or satellites or GPS system. Hospitals, gas stations, and everything else we depend on so much could not work in proper way. There could be regional or even global blackouts. But worst of all, that there would be such panic that would cause the greatest horror. But there is good news, don't worry. With our advanced technology, we can predict space weather. That is, we may know when a major CMA takes place and is launched towards Earth. However, we don't know exactly how great it would be until it reaches us. Nevertheless, we can prevent global damage by shutting down all the systems possible. Because it's better to make a blackout for a few days than to suffer the damages for several years. And finally, how do magnetic storms affect human body? The scientific doctrine says that in no way. And it is absolutely true, because particles from the sun do not affect us. We are protected by our magnetic field and by atmosphere as well. But we are not separate organisms from the Earth's magnetic field. Our brains, our heart, operate with electrical impulses. Metal ions flow in our cells. Magnetism does affect these. And experience show that in times of magnetic storms, there are more cases of blood pressure fluctuation, heart problems, sleep disruptions, anxiety, and other things. And one more thing, those who think that celestial bodies do not influence us, do not have any metaphysical qualities, think of magnetism, which envelops the whole solar system. And now you can say that Mars, for example, has no magnetic field. It is true because its core cooled long ago. But still, it does have an induced magnetosphere due to solar wind. So the magnetism radiated by us and others and all celestial bodies do interact. Thanks for joining me in this complicated episode. In the final chapter of the Sun trilogy, we'll deal with how the Sun reached its current state, that is a main sequence star, and what its destiny will be in future.